Good morning. Sunday morning lead off in Las Vegas. Everybody's worst nightmare. I will try to keep it lively. So I want to take a different survey. This is a bit of an introspective question for a Sunday morning. Who in the audience considers himself a geek? Honest, please. Okay. Just want to get the tone right. So I'm going to talk a little bit about why you're here and the journey the company's on. As you heard, up until last spring, I was part of the Watson organization, productizing the Watson platform, and I was asked to come back to research and talk about and figure out what the next thing should be, and that's what I'm going to talk about today. So I'll talk a little bit about a research agenda and how we think cognitive computing will impact you, but mostly it's a research agenda. I'm a researcher, so it's my prerogative, and you'll hear more of it during the research track this afternoon, and we have a whole day tomorrow. So why are you here? This is why everybody is here. Basically, we believe that cognitive computing and AI technologies are going to pervade everything that you do kind of from this day forward. It's a pretty profound statement. It's one of the most dramatic changes in computing technology that I've ever seen, and I've been around a little while. So things that we do relatively routinely are going to change. As an example, we've been experimenting with Hilton Hotels. We have a robot concierge in pilot called Connie, named after Conrad Hilton, the CEO. And Connie's there to help. So Connie might ask you, because Connie can see you, notice that you're puzzled, are you looking for the elevator? If you're a business type and you're worried about what kind of investment decisions you might make, systems like Watson and others built with these technologies are very good at ingesting content from a variety of sources. And you can use systems like this for decision support. You can ask questions about product overlap, or you can ask questions about regulatory compliance. We're doing a lot of work in elder care, as are others, using AI technologies to help people. So, for example, robot concierge will notice that you're confused and tell you where to find your medication. And the one in the middle on the left, I have a personal interest because I am going hiking in Ushuaia next April, and I'm going to want to know what to wear and what to do. And the experience that I've been having has been not good, so I actually look forward to technologies like Watson being a lot more functional than they are today. Today, the joy of figuring out what to do on a vacation requires pawing through commerce websites and travel websites. Not exactly a cognitive experience at all. So let me talk a little about how we got here and where we're going. Early AI systems, and I'm going to date this as back in the 70s, did some pretty interesting things. The one on the left was a system that Terry Winograd built called Sherdlu when he was at Stanford in the 70s. And what it did was it reasoned about blocks. System in the middle called Aaron is really about creativity and art. And that's a fascinating space that's continued to this day. It's really about how creativity works, and the system came from UCSD. The one on the right from Carnegie Education is a teaching assistant. Some of you may know that we've taken a big bet on cognitive education at IBM. We've formed a Watson education unit. So other kinds of research that people have been doing for a long time have been about gaming. Games provide, aside from distractions, a great laboratory for reasoning. 3 of those actually came from IBM. People don't know that we have that much interest in playing games. Well, those who work at IBM do. Those who don't do not. So Arthur Samuel built a checkers program that ran on the IBM 701 in the 50s. Checkers systems have downsized quite a bit since then. The Deep Blue game between Garry Kasparov and IBM is there. And Jerry Tesaro on the top right built a system to learn to play backgammon. What's interesting is all 4 of these were systems that were about learning, even though, for example, the Deep Blue chess program did something called an alpha-beta tree search. It actually learned over time what good moves were, knew how to reason about different parts of the game, and used machine learning to figure out what to do. Most recently, and the most interesting recent one, because of the complexity of the game, was AlphaGo from Google's DeepMinds beating the world champion at Go. And the reason that's interesting is because the game is so complex, the state space of moves is so big. Well, the Watson back in 2011 was really a different thought. The other games were about reasoning, well-understood spaces. What Watson was about understanding natural language and being able to answer questions. It's the outgrowth of a lot of research at IBM over the years in a domain called deep question and answering. The research problem is very simple to state. Can we teach a system a domain and then have it answer questions? Sort of a variant or a simplification of the Turing test. So that's where Watson was in 2011. We've come a long way since then. Today, Watson is a set of APIs and RESTful services that are cloud delivered that do question answering and a lot of other things and continue to evolve. So we're building, if you like, a cognitive toolkit. And the expectation is people in this room, at least the geeks, and others will build Watson applications using these APIs. So why now? People ask me that all the time. I'm going to spend a couple of minutes talking about why now. First of all, there's a lot of data out there to train systems like Watson. Up until Watson was demonstrated, if you like, most of the training for AI applications used relatively structured information sources. And Watson was probably one of the first systems to do a wholesale reasoning capability based on unstructured and uncertain data. Well, if you look at this graph, the amount of unstructured and uncertain data is exploding. We've all seen this picture. So you'll hear about Internet of Things later today. We'll probably talk about social media, voice over IP. These are all sources of information that can be used to teach cognitive systems. The idea is to extract signal from all of that data out there, build a knowledge base that approximates the data, and make decisions. So as to why now, I sort of see 3 things, and they're all around being able to deal with massive amounts of data. First is cloud. What this is letting us do is scale these systems tremendously and really co-locate the data and the applications together in the cloud. The other thing that's been remarkable to see has been the emergence of deep learning as a training technology. There's a variety of different classes of neural networks for doing things like transfer learning and classification. And they seem to provide I guess I should say this, a way to train systems that is relatively universal. Prior to the advent of deep learning, there was a complex process called feature engineering where smart people would transform the data to extract bits and pieces, and then they would learn about those bits and pieces. What deep learning does is figure out what those bits and pieces are in general. One simply encodes the data in a very, very high dimensional space, runs it through these networks forward and backwards again and again, and models emerge. And the codification is less about the feature engineering and more about here's a good neural network for speech, here's a good neural network for classifying images, here's a great neural network for translating or generating text. So that's where we are today. Now, where I think we're going is really climbing up the value chain. Most AI systems, I don't care where they come from today, look kind of the same. What they do is they take a bunch of content, train models, then you write code that uses those models to extract content from queries, and then you write code that interacts with the things that you've extracted. So if you're writing a medical application, you might have a model that knows how to extract things about disease or medication or genomic pathways from input. And then you'll write a program that knows about oncology, like we have, and can reason about the extracted artifacts. It's very brittle. So the necessity is to really be able to teach AI systems to reason about domains and not just be able to process signals. And it's a combination of logic, learning, and probability. We call it probabilistic reasoning. And it really is bringing the AI systems of the 80s, which were highly rule-based, together with the systems we've been building recently, which are statistically based. Now, there is a lot of heavy lifting. I'm going to spend the rest of the talk talking about the heavy lifting that is going to be required to get there from here. As an example, one of the technology areas that people have been working on for a long time is about interpreting medical imagery. And the reason is very simple: eye strain. Radiologists and cardiologists spend the day being bombarded with image after image after image after image. Most of them are irrelevant. And mostly what they do is get tired. Once you're tired, your ability to do a good job degrades. So you can see that really in about 2013, we started building systems that were as good as people. Now, this doesn't mean that all cardiologists should retire and hit the golf course. What it means is we can, instead of giving them 50,000 images from an examination of a patient, we'll give them 15, and they'll look at 15 images to see what has to happen, and their capacity goes up. And the quality of their work goes up as well. Other areas where we've also seen a lot of progress are speech. For years, up until the advent of neural networks, speech recognition systems hovered at around a word error rate of 20%. And what that means is that 20% of the words in a spoken passage were recognized incorrectly. You can see the huge drop once neural networks were introduced. And there's actually been some progress recently. Team at IBM announced a word error rate of about 6%. Team from Microsoft, I think last week, announced a word error rate of 5.9. So we're getting close. The idea is to get to systems that perform as well as people, so that you can put a speech engine in a car or in an airplane cockpit or in a courtroom or in an operating room, wherever you need one. Now, these new kinds of workloads, and I've listed some here, are computationally very expensive. This chart talks about really the relationship of the task complexity, how much data there is, and what the computational costs are on them. And the university folks in the audience recognize this, and a lot of them are looking at making this work better. So how can you make deep neural network training work on larger data sets or larger models? Neural network models have been increasing at an enormous rate. Graph analytics is another one. A very common way to represent information is through what's called the graph database, which is a graph full of entities, things, and their relationships. These things get enormous. Billions and billions of entities and relationships. I feel like Carl Sagan. And the computational cost is such that these things can't be held in memory anymore. So how do you process them? And I could go on all of these, and there's others I haven't listed. But the point is, there's a bit of a renaissance of what we used to call data structures and algorithms works, specifically focused on the kinds of workloads that we see in cognitive computing. Another example is open data. Linked open data has been exploding since it really came on the scene early in the millennium. And these are enormous collections of triples, billions of them, which you can use to train a generic machine model and then use them. So if you're going to create a model that has common knowledge in it, you'll have to create a model that knows how to deal with, almost 1 trillion triples today. That's a lot of data, actually. The other thing that comes up when you think about that, and when you think about the sizes of cloud data centers, is how to cool them and power them. The joke about large data centers being co-located near large hydroelectric plants to get the cost of electricity down. If you put them in a northern climate, they're easier to cool as well. So this is happening. And this is why. If you look at this particular problem, which is image recognition, what we did is we did a bit of a study looking at how we could take a generic CPU, a normal central processor, and add GPUs, FPGAs, and see how much more energy efficient we got. So the chart is how many bits have you recognized per billionth of a joule. And that's a log chart, by the way. So the one at the top, which is a piece of work I'll talk about later called IBM Synapse, is 100,000 times more efficient than a server today. And that's a huge, huge, huge number. It goes to scale, it goes to speed, and it goes to, frankly, the cost of computation. When you think about building this class of algorithm, there are two things to think about. Number one, how long does it take to write the application? And that's a statement about people time, developer time. The most expensive resource during development of these algorithms is people. So anything that you can do to take people costs down through tools, algorithms, methodology, whatever, will help. Once the thing is deployed, the only thing that matters is two things, cost and latency. So the cost has to be sufficiently low that you can run the thing profitably for the amount of money that you're going to get for working on the problem. And it's got to run fast enough. That's why things like energy efficiency are so critical. So I'll talk a little bit about what we're doing. Roughly speaking, I think about cognitive computing at 4 layers: systems infrastructure, cognitive services or APIs, frameworks where you put collections of them together to build applications, and you'll hear more of that today from other speakers, and finally applications at the top. I'm going to focus mostly on the technology for the rest of this talk. So first thing systems have to do, and I said this, understand signals. Typically today, speech, images, videos, and text. You need to be able to train them fast, accurate, dynamic, which means these systems have to learn on the job. These systems, as you use them, have to get smarter, which is about different kinds of supervised and unsupervised learning. You've got to understand the content, so it's not just enough to read it and train the systems. You've got to be able to understand it, build structures from that data, whether it's text, images, videos, or spoken speech, and create structures that admit people to write applications on them. And you need to be able to create things too. So there's a lot of work going on in what I call the bot wars worldwide. Everybody's building bots. You can't look under a rock without finding a bot nowadays. We are too. And the challenge with these systems is traditionally they've been fairly brittle to train. You know, if you say this, then say that, and do this. That's a old school rule-based way of training systems like this, and it's got to be better. In the same way that we have taught systems to understand content, we have to teach systems to understand conversation and learn from them. So what is an example of what it might mean to put all this together? So here's an example of a system that's currently in the research labs. It takes as input a pile of documents, tables, financial reports, SEC filings, ingests them into a knowledge graph, and then you can ask questions like, you know, show me the revenues of a bank, and what the system will then do is render the result like that. Prior to that, the ability to answer a question like that requires looking through reports, doing arithmetic, web searching, and it can take weeks. Revenues for Citibank between 2009 and 2015 is actually a hard one. Banks have lots of subsidiaries, operate in lots of different countries. The reports are in lots of different languages. There's a ton of work to do there. So that's, if you like, one set of activities that never ends, making signal comprehension more accurate, make it faster, learn on the job, merge them. So the ability to analyze video is about running two channels of analysis together, which is audio and video. Then you can do things like keyframing. So I want to talk a little bit now about where I think things are going. This is an area we have a lot of focus on at IBM, as do others. And I call this the kind of the reasoning stack. And roughly speaking, from left to right, we learn, and really this is about research and machine learning. How do you scale models? Models are getting enormous. You have to be able to train them, again, fast enough. You have to deal with more and more and more training data. Conversely, a lot of machine learning problems, you're looking to build a model where you don't have much data at all. How do you do that? Right? One of the things we know about deep neural networks is they take enormous amounts of data to be trained. That's not always going to be the case. And there's lots of work going on hybrid models, neural networks with memories. They look a little bit like Turing machines. And causality. So we're really good at reasoning about correlation. This and this are correlated. But how do you reason about this causing this? So the ability to reason and create machine learning models that have notions of causality in them is really important for decision making. If I think about knowledge extraction, which I talked about before, this is where a lot of the kinds of inference that I talked about come up. Symbolic inference, to be able to reason about facts. So mixing general knowledge with what we know about a particular company. Approximate reasoning, probabilistic reasoning, and symbolic inference create a stew. How do we put them together? And the other thing that we need to do is help subject matter experts translate what they do into building models about a domain. And that's actually a very, very difficult problem. If you go talk to a doctor, and I have, about how they know what they know, or lawyers are even better. Any lawyers in the room? Oh, good. No lawyers. Okay. Okay. So it's really fun. If you actually work with a lawyer, you can try this experiment at home, okay? Go to a lawyer, and lawyers are really good at answering questions. You ask a lawyer a question, and they'll give you an answer. usually it's no, but sometimes it's yes. Okay. Now, if you ask a lawyer to help you build a model for decision making, how did they get to yes and no? They'll look at you like you have 4 ears. Okay. And that's the challenge with subject matter expertise. A lot of experts have built up a knowledge base over the years, and they don't actually know how they know what they know. And the challenge of building models of deep domain knowledge is about codifying that. As an example, when you put all of these things together, there's some simple things that seem hard, but seem easy, but are pretty tough. What semantic information is in a document? So in order to figure that out, you have to take the document, you have to chop it into pieces. You have to be able to interpret pictures, you have to be able to interpret graphs, tables, text, and put it all together in order to be able to reason about that. So this is, if you like, infinite homework problems for graduate students, because think about the notion a picture is worth 1,000 words. It's actually the other way around for artificial intelligence systems. We're really good at words, we're not so good at pictures. So there's work here. Let me talk about querying and retrieving information just for a minute. 2 real aspects here. One of them is what we call fusion. And the idea is to, and we did this in Watson as well, if you have a question to be answered, a problem, a classification to be done, and you're not quite sure whether technique A, B, C, D, E, or F works best on this problem, use them all. And then use machine learning to figure out, for this particular problem, you build out a model to say when to use A versus when to use E. Okay, we call it fusion. And learning on the job is critical. This is about systems using mixes of supervised and unsupervised learning to get smaller as they're used. And it's a bit of a tricky process. Some of you may remember the Microsoft bot named Tay that was hijacked in a fairly ugly way. And the reason being is there were no guardrails put on the deployed machine model. So it learned what it learned, as opposed to saying, that thing that people are telling it is true is probably a little far away from what it already knew, so maybe we should discount it. Lots of work there. Reasoning and planning. Planning has been an area of research for many, many years. So is machine reasoning. So building reasoners that mix textual reasoning, symbolic reasoning, hypothesis-based planning, so systems that help you plan scenarios and understand them and decide whether the scenario is possible and how possible come up all the time. Deciding whether I should make a business investment is really a planning discussion. So understanding the impact of making a particular decision is another AI problem. And lastly, decision support. Oh, pardon me, I'm out of order here. As an example of reasoning, here's a simple one, right? I'm interacting with a call center bot and I have a very simple question. How much is my monthly payment going to be? In order to answer that question, the bot has to have internalized how the financial institution calculates payments, and that's a comment about what I know about the client and what I know about the policies of the company. So how do I teach a system all of that information in a way that's generic? Again, this is about teaching these kinds of systems to do math in the context of interacting with people. And lastly, decision support. Recommendation engines, collaborative decision making, and lots and lots of industry use cases. As you climb up the stack and talk about decision support, you're really about, should I make this investment? What treatment should I give? You're really at a very high level in terms of reasoning about an industry. And we've been working on generic decision support for a long time. We've got a research program we call computational argumentation, and it's really about the computation of arguments. How do you construct arguments based on a set of evidence that are supported or refuted by the evidence? And how strong are those arguments? How do you weight and measure arguments? Sorry. If you can solve that problem, then you can do a lot of the reasoning needed to make decision support at an industry level. So that's track 2, reasoning about domains. Next, I want to talk about interaction. These systems all work with people. So the ability to create APIs and services that know about people's personality, their interests, their cultural background, their mental and physical state. Are they happy? Are they sad? Are they frustrated? Are they pissed off? Okay. All of those things are needed if these systems are going to interact with people in a cohesive way. The other thing that's important to understand, these cognitive technologies foundationally are going to change the way we interact with computers. And it's not trivial. If you think about we've all had experience dealing with bots on the phone. Some of them work pretty well. Some of them make us want to throw the phones against the wall. What are the new patterns of interaction when you move from a person controlling a system to a system sensing something about the user, advising the user, the system being confused about what the user is saying and being able to ask a clarifying question? Suddenly we're having a conversation in a way not dissimilar to how people interact. So there's a lot going on here. And my view is that we need to understand what these new patterns of interaction are. We also have a research area we call embodied cognition, which is really about taking these cognitive capabilities and putting them in physical things, robots, rooms, avatars, objects. And the idea being that embodiment is fairly complicated. It involves models of a domain, excuse me. Models of a domain, planning, action planning, sense and respond. We're trying to build a toolkit to make it easier for people to build these kinds of complicated systems. And conversation, I talked about bots. Contextual understanding, action planning. So understand the context of a conversation. Have I talked to this person before? What do I know about this person? What do I know about what they've been talking about? When they refer to something in the past, I need to know what it is. And then that's really about learning sequences, tasks, learning words. So we're really combining rules. If people say this, then do that, with task learning. So we're really building these rules dynamically, and these rules change as a result of contextual understanding the system has. And context. What do we know about the person? So that's interaction. So I want to talk about systems a little. We've been building computing systems for a very long time. That thing labeled 1900 plus is a computer card, and they were originally designed to do things like tabulate the census, counting votes, when it became too expensive to do it by hand. So computing systems were about hardware. Build a machine to count things. That went on for a long time. In the 50s, we started building these things called stored programs. Any COBOL programmers who are willing to admit that they're COBOL programmers? Okay, you want to tell everybody what that is? You need glasses and, your eyes may be, no? Okay, that's Hello World in COBOL. I had a phase too. So from the 1950s on, we were writing algorithms. Today, and I dated it from 2005 on, things have changed. We're not building programs so much as we're taking programs that learn and we're training models. And it is a completely different way to program. And that's what all of this stuff is about. It's about a sea change in computation. This notion of a computer model is a bit of a new animal for all of us, whether you're a software engineer, a data scientist, or a systems administrator. You should be asking questions like, how do I secure machine models? Does it behave like data? Does it behave like a program? How do they behave? And how do I coordinate the life cycle between building applications, which we understand, or building services, and building models? What tools, what methodology are there? Well, tell you a story. There was a team at, anybody here from Ithaca? Okay, Cornell Tech. They demonstrated how you can steal models, right? Just by querying them. You query a model. So what a machine model is, by the way, is it's a response surface in a very high dimensional space, and determining what this model tells you to do is about telling you which point on the response surface is closest to your situation, okay? So if the response surface represents language in law, and you give it language, you give it a sentence, the job of the model is to tell you what you're talking about in legal terms, and that's about finding things that are closest to us in this law language, million-dimensional space. Well, if you query that model enough times with enough random sentences, you know what the answers are because you've asked it all the questions you can ask. So you can steal models. Okay. Well, I talked about the Microsoft example. You can pervert models. So we have to think about these models as existing not in a benign space, but in the wild. And we have to understand how to secure them, train them, and maintain them. This is, by the way, a shout out to the academics in the world and the room. So this combination of cloud and deep learning, which I've been talking about, there's a whole lot going on here in terms of putting deep learning in the cloud so it's fast. What are the new classes of accelerators? What's the analog of a GPU for training, or the analog of a GPU for inference for machine learning? And as I talked about, how do you secure models and how do you secure data? So one interesting example of a system that we've been working at IBM on for a while is something called Synapse. This is pretty cool. It's a computer chip, big one. And instead of having a standard, if you like, Turing-based or von Neumann instruction set, it's got a neural network as the instruction set. So the instructions are about neurons and spikes. Okay. So you program it by taking your favorite machine learning model framework, whether it's TensorFlow or Caffe or Torch, and we'll translate it into the compile it, if you like, to run on this machine. And this is the one that has the performance at about 100,000 times better than a CPU for image processing. So this is an example of a new kind of cognitive accelerator. So this is what we're doing at IBM. It's sort of taking you through where we think the problems lie, the things we're working on, and the kinds of technologies that you'll be coming back here to learn about next year and the year after and the year after that, and the technologies that you'll be using as well. So as an example, and this is an example from a team in our Haifa lab, putting all the pieces together. This is an augmented reality system for a field service professional. So the system has been trained by reading manuals about the parts in the systems and the processes for repair. We're using analysis, image analysis, to figure out what they're looking for, looking at and matching it to what the system knows about. We're using speech recognition, so the individual who probably has their hands full of electronics can talk to the system. And we're generating speech, we're generating instruction, we're generating pictures to show them what to do. Okay? So, as I said, these systems are changing, they're changing rapidly, and these technologies are popping up in all sorts of interesting places. Thank you.
All right, there we go. All right, so we got 5 minutes for questions. Because it's a big room, I'm going to ask that you come up to one of these mics to ask your question. And then when we're done with that quick Q&A period, you can continue and meet Michael outside and if you have more questions. And then I'm going to have a little bit more logistical update, and then we'll break and go to the other session. So thank you.
Hi,
hey.
Thanks for the presentation. Many companies are investing in AI today, and I just wanted to know whether the technology is similar, or different, and in what ways Watson is different to our competitors.
At the technology level, not too different. So if I talk about research as an example, we all go to the same conferences, we all publish papers, we all argue with each other. So at the foundational level, the technologies are not hugely different. I think the thing that differentiates IBM, and it's not so much Watson, it's IBM, is deep domain understanding. So people ask me about Siri all the time, are you as good at Siri? And, or Cortana, or API.AI, whatever it might be. And these systems are fairly fixed. They do what they do very well. They're deeply integrated systems. I have 2 Amazon Echoes at home. And what's remarkable about Echo, the speech recognition is actually pretty lousy. And you can find out, there's a command you can give Alexa to have her tell you what she thinks she heard. But they've done a pretty good job on keyword matching and integrating that keyword matching with plugins that companies write, so you can't tell. So if you're going to build a verticalized application in a specific domain, whether it's navigating a car or helping you diagnose why your phone doesn't work, or adding stuff to your shopping list, or banking, or jokes, whatever it might be. If you deeply integrate that application, you're going to do a good job. Where we're focused is in a different place. We are focused on building. We deeply, deeply believe. Remember I said that half of the applications worldwide are going to be cognitive in a couple of years. Well, we're not going to write them all. No way. I mean, IBM can't even spell consumer, although we bought the weather company so we can maybe get it right sometimes. But mostly, we're not a consumer company. We're an enterprise-facing company. So we know that we're not going to write all the applications in the world, nor do we want to. So our goal is to build this toolkit of cognitive tools so that you can. So the combination of making sure we understand industries in a deep way, so we build platforms that are appropriate for healthcare or education or Internet of Things, and working with those who want to build applications is kind of why we're a little different. Okay. Other questions? Yeah.
You mentioned that lawyers have this problem of not being able to tell you why they came to some decision, and deep nets have a similar problem. How important do you think that is for us to be able to figure out how to make those algorithms that will translate so they can give us some bit of understanding so that we can begin to have trust in the analytics that come out of those machines when they're solving important problems?
Yeah, I should have paid you to ask that question. Thank you. It's a good one. So there is a lot of work going on what I would call evidence-based artificial intelligence. And deep neural networks are a really good example of black boxes, A lot of the work that we've done, and the reason Watson uses techniques other than learning, we use deep learning as well, is to be able to provide evidence. We know that whenever you want to ask a system why, it'll tell you, or an expert will not believe you. So one of the, I should have mentioned it, but one of the broad research areas that I see is about being able to add evidence to deep learning kinds of training. It's a hard problem. Next question.
Yes, sir. In the Marine Corps, we're looking at possibility of adopting cognitive assistance of this sort. And one of the things is the assistant would have to be the leader or the Marine would have to have as much confidence and comfort with the assistant as it would with another Marine functioning in the same way. And Marine speak is a real thing. It's a part of our culture. And it's highly abbreviated.
Yeah.
It's nuanced. And often what is not said in context has meaning in itself. And will these capabilities, these machines, be able to adopt those sorts of nuances? I know some of it has to be oriented on the person and some memory of the person, but we have a very imperfect lingo in the military, but it works very efficiently and it makes us very comfortable. I'm wondering how the machine can deal with that.
First, thanks for your service. There's about 4 parts to your question. So number one, the lingo. So one of the reasons we've been working on speech technologies at IBM for years, and if you look at companies who are building bots, all of them are making investments in speech. And that's so that they can train these systems to recognize the language. And we can. One of the reasons, back to how we're different, is we open up the ability to take and train the system to understand very, very specific language. And, you know, Armed Forces lingo is actually a really good example. So that's one. The next one is actually, it's not so much that Marines are different in the sense that they want to trust a system that they interact with. Everybody does. And that's about building a system by working with people who really understand how Marines think, so you can codify it. Again, I talked about industry expertise, and working at an industry level is a critical thing to be able to get this right. The only way you're going to get it right is if you have Marines helping you build the system. So you're absolutely correct. Are we done?
Yes.
Okay. Everybody,
All right. Thank you, Dr. Karasick.